Hi, now I will talk about motion of a particle under a constant force. Consider a particle of mass m subjected to a constant force F. A constant force F means it should maintain its direction as well as its magnitude same throughout the space. Now for simplicity we will consider this as a case of one-dimensional problem. The force which we are considering here B F into I cap means its magnitude is F and its direction is I cap and it is subjected only along this x-axis. Now wherever you go along the x-axis the force will be same. It will be given by F into I cap. And now consider a particle of mass m which say at time t equals to 0 be at rest in the origin and is subjected to this constant force. Then under this constant force the particle accelerates along this x-axis, and our motto is to find out what will be position of this particle over a time, means for a given time what will be the position of this particle that we are supposed to find out. Now the case consideration of one-dimensional is just for simplicity. And now since the problem is in one-dimensional one, we can drop the vector signs in further derivation. Now the initial condition B at time t equals to 0, the position of the particle is 0, means x of 0 is 0. It is at origin. Now by definition of relativistic force, the relativistic force is defined by dp by dt. And now by rearrangement it is dp equals to f into dt. Integrating it on both sides you will get p equals to ft plus constant, because since f is constant it is easy to integrate it. It is just p on this side and t on this side, and this constant is a constant of integration. Now we will consider another initial condition that at time t equals to 0 the momentum of the particle is also 0, means initially the particle is at rest at origin. It is just for simplicity we are considering this. So then if you substitute t equals to 0 and p equals to 0 in this equation, you will show that the constant must be also equals to 0. So then if you make that constant 0, then the equation will become p equals to f into t. Call this as equation 1. And p is given in terms of ordinary velocity u by this following expression. This we have already derived out. And p equals to mass into the ordinary velocity divided by 1 minus u square by c square. So now from equation 1 and 2 you can equate this, because p is same in both. You will see mu by square root of 1 minus u square by c square equals to f into t. Now you can square it on both sides, means this expression you square it on both sides and rearrange it and take out u out, and you can express u in terms of the force, the time, mass and the velocity of light, and you will get u as equals to f by m into t by square root of 1 plus ft by mc square. Now this is the expression for velocity of a particle at any given time t. Since the velocity of the particle goes on increasing because it is subjected to a force, hence its velocity also should increase further. As time increases, its velocity also increases. So now the numerator means this one, fm by t, is actually a classical answer for the velocity. Means it's approximately right. If f by m into t is very less than c, means the force involved is very small and mass involved is large, then f by m into t is very less than c, then in that case you can substitute ft by mc equals to 0. And in this expression if ft by mc is substituted to 0, then you will see that u equals to ft by m. So that's what we are telling. Ft by m is a classical answer, and you can see that in classical mechanics the velocity is given by acceleration into time. If the initial velocity is 0 and if the initial position is also 0, then the velocity is given by acceleration into time, and acceleration is given by force by mass, because force equals to mass into acceleration. From that, this substitution, F by m into t, that will be the velocity of the particle. And here also we are getting same thing. If you substitute Ft by mc in this expression, you will get it as Ft by m as the velocity of the particle. Hence, what we can say is, in the non-relativistic case, the expression which we just obtained here, the u expression, will reduce it into the classical expression for the velocity of the particle subjected to a constant force. Right. Now, in this expression, the denominator part will take care of the fact that the velocity can never exceed the velocity of light. We can see it here. Now, the classical velocity expression says that if you go on increasing t, if t is tend to infinity, if t goes to infinity, then u also goes to infinity. Means as t becomes large and large, u also will become large and large, and at one time it may cross the velocity of light. That is a classical expectation. But the relativity says it's not possible. And in the relativistic expression of u, this denominator part will take care of that. It will limit that the velocity of the particle can never exceed the velocity of light. You can see here, you substitute, you put the limit t tends to infinity in the expression of the relativistic velocity equation here. So now we will do that. Limit t tends to infinity for this expression, and take t common from both numerator and denominator. And since you are taking t common out from a square root, then it has to be t square here, and then t cancels from them, and limit applies to only 1 by t square. Now if limit t tends to infinity, then 1 by t square tends to 0. So then the expression will be just f by m divided by f by mc, because there is a square and there is a square root, they will go out, and f by m. And here also f cancels, m cancels, and c go up, and you can see that limit t tends to infinity u is actually the velocity of light c. So the relativistic formula takes care of this. Means it will take care also that in the non-relativistic domain it reduces to a classical formula. As well, in the relativistic case, if t tends to infinity, if you make it large and large, the velocity of the particle tends to velocity of light instead of tending to infinity. It's really an interesting thing. So it puts the speed limit for the particles. So you can see that in the particle accelerators, in the charged particle accelerators, the charged particles will be put in the beamline, and they keep on accelerating it under applying a constant electric field, or by varying magnetic field, they can go on accelerating. You can expect that if you go on accelerating for a large amount of time, the velocity of the particle may cross the velocity of light, but it is not possible. The relativistic formula shows that however long you apply the force on the particle, the velocity of the particle can never exceed the velocity of light. It will just tend to the velocity of light c. Right. So now with u equals to dx by dt, you can go back to this expression for u and change u by dx by dt and rearrange it, and you will get it as dx equals to fm by t by square root of 1 plus ft by mc square into dt. Now for the solution, means we were interested to know what is the position of the particle, that is x, at a given time t. Now we are interested to know x as a function of time t. Now to get it, you have to integrate this expression. So now we will do that. So when you integrate it, the left hand side will become just x, and the integration for the right hand side will go from the limit time 0 to some time t. So now to integrate this is not a big thing. You can substitute 1 plus ft by mc square as some variable alpha or something. Then you can differentiate on both sides and substitute the variable, and you can show that the integration of this is this expression. Now we will apply the limits time t equals to 0 and time t equals to t. Then if you do it for limit t, it is the same expression. For the limit 0, it is, if you substitute 0 here, then this block will go, then square root of 1 is 1, then it is minus 1. So hence x of t is mc square by f into square root of 1 plus ft by mc square minus 1. This is the expression for position of the particle at any given time t. Now if a particle is subjected to a force F, and if the particle's mass is, rest mass is m, and the velocity of light is c, then at any given time t, if you are interested to know what is its position, then you have to just substitute t here and it will compute the position for you. And now corollary to that one, the classically what is the position of the particle subjected to a constant force? Classically, the formula for the position of a particle is s equals to ut plus half at square, where u naught is the initial velocity, t is the time, and a is the acceleration. With Newton's law, F equals to ma for a constant force F, and you can take a equals to F by m, and you can substitute it here, and we took as the initial condition u naught equals to 0. Hence we will remove this first block out, and we are left out with only the second block, half at square, and here you substitute a by f by m, and then you will get it as the position x as f by 2m into t square. This is the classical answer for the position of the particle. Right, so now you can see that in comparison with these two expressions, the classical expression expects a parabola in a graph drawn between x and t. Means in Minkowski space, we are going to draw graphs between the position coordinates x and the time coordinates t. If you plot the graph, this expects a parabola. The classical answer expects a parabola because it is x equals to some constant into t square. It is an equation of a parabola. But the relativistic expression is not a parabola, it is actually an hyperbola. This is an expression of an hyperbola. So now if you use these two and try to draw the curves, trajectories in the Minkowski space-time, then this is the classical parabola and this is the relativistic hyperbola. You can see that as time t increases, this curve will tend in such a way that its slope will go on converging it into the slope of the word line of light. So this dashed line is the word line of light, or it is for the light, you can see it's 45 degrees, it's angle made with this, and the slope is 1, and this relativistic hyperbola will asymptotically make it in such a way that the slope of this curve at any given point will tend to the slope of the word line of a photon. Instead, the classical parabola is like this. You can see here at any point here, if you see the slope for the tangent of this curve, this will be the tangent of this curve, and you can clearly see that the slope is less than the slope for the light, which is not possible. So of course the classical answer is incorrect. But you can see that in the non-relativistic domain, means in the lesser times, lower velocities, you can see here both relativistic parabola and the relativistic hyperbola and classical parabola are nearly same, are going hand in hand. But after that, as the speed increases, they split apart. They show two different trends, and among that the relativistic hyperbola is the correct one, which is the expected one. So hence we sometimes call it as an hyperbolic motion. We call it as an hyperbolic motion. And this kind of examples occur in the charged particle accelerators, as I explained before.